So we have the pleasure of having LSchmitz. This will be more experimental.
Thanks very much. Thanks very much to Guilherme for accommodating the talk at the last minute because the D3D schedule was somewhat unpredictable this year. And I only knew today, so 3 days ago, that I could come. So this talk is about potentially the drive of zonal flows and associated problems creation by multiple alkane eigenmodes that travel by fast particles in these domains. So conventionally, the idea is that alpha particles transfer energy to the fuel ion here. However, the experimental observation was that alpha-driven alkane eigenmodes that are also called fast ion losses. And in addition to transport losses, there's also the concern of having 3.5 MeV alpha particles hit the wall and then create an undue amount of erosion there. The question is now, since the work that has been going, both theoretical work, modeling work, and simulation work that has been going on since about 2000, has predicted that alpha alkane eigenmodes can also drive zonal flows that potentially improve plasma confinement. So the question is, can we make up for the loss of fast ions due to energetic particle modes by increasing the ion temperature to improve thermal plasma confinement? And this is very much an unresolved question. So what I want to do here is first introduce briefly zonal flows and also the particular diagnostic that we use to measure zonal flows in the core plasma. And then I will look at intermittent alkane eigenmodes that we observe in plasmas with relatively high ion beta, about 3%, that trigger intermittent shear flows, and then associated with that, there's microturbulence suppression of the thermal plasma turbulence, ITG and TM modes and the like. And there's essentially evidence for localized axisymmetric, so colloidal and toroidal mode number equals 0, reversing shear flows to the plasma core around 4.45, plus minus about 5 centimeters. So localized shear flow layers are created. And then in the second part of the talk, I want to go into radial profile measurements, propagation dynamics, and then some address causality concerns a little bit in a preliminary way. This work that is very much ongoing. The whole work that you see is only a couple of months old, so it's very new, and the analysis is very new. So we look at radial profiles, causality, and Reynolds stress dynamics, and then as an outlook, future work, comparison to theory, and so on. So in a nutshell here, this is the experimental result that most of the talk is based on. We observe basically intermittent multiple Theorie eigenmodes. You can see here that there's a banded structure that's different frequencies here between about 150 and 240 kilohertz. And these are modes that essentially can nonlinearly interact and create shear flows. So this is the integrated amplitude of these Theorie modes that appear intermittently, just measured over this frequency band here between 150 and 200 kilohertz or 240 kilohertz. And then what you see.
Sorry, very naive question. What are the colors? What is being plotted?
Oh, this is basically the amplitude. It's a contour plot of the amplitude of the density fluctuation associated with both the broadband turbulence here and the TAE modes. So it's measured by beam emission spectroscopy that can actually produce a signal in a 8x8 array that is proportional to the density fluctuation. So then, this is basically the amplitude of the TAE modes here. So this is what's in the frequency band. And then this is the amplitude of the background plasma turbulence, ITG-TM modes. And that's measured by Doppler backscattering at the same radius, 0.43 here. And what you see is basically when you measure the frequency shearing rate by using two closely associated channels, and I'll show you later on a little bit more detail how that measurement is done, that basically whenever these modes flare up, the shear flow increases here. And so it peaks about at the end of the phase of the active PE modes here. And at the same time, the fluctuations in the background turbulence drop. So there's basically this almost perfect anti-correlation between shear flow increasing and turbulence going down. And this happens essentially to be stimulated by these events, alpine eigenmode events that we see here in the PES spectrum. So looking at this in a little bit more detail now, essentially, in terms of background turbulence, the thermal kinetic gradients drive IPGPM and other modes here, both in the ion and electron range. And in turn, these modes create thermal transport that change the gradient. So there's an equilibrium established essentially between microturbulence drive and thermal transport. Another important player in this is the zonal flow that creates essentially a feedback loop. So the drift brake spectrum can drive axisymmetric zonal flows that in turn react back and shear the turbulence. So there's another separation mechanism or a limiting mechanism that occurs because of these axisymmetric flows that have been demonstrated in many devices. And they are characteristically mesoscale in the radial direction. So they are basically axisymmetric in the colloidal-toroidal direction. So the colloidal-toroidal mode numbers are zero, but the KR can be very large. So they can be very localized on the order of radial lengths between the ion-Lama radius and the macroscopic density or potential temperature gradient length. When we consider fast particles, there's now additional complexity coming in because there's now an additional driver that is the fast particle kinetic gradient that can create instabilities that are generic to fast particles. In this case, towards the use of eigenmodes, that's the modes that I showed you on the previous slide. And they in turn can create transport of fast particles. But they can also generate shift zonal flows and in turn be sheared by zonal flows. So now you have basically a dual feedback loop. You have the drift plates on the flow system and you have the PE zonal flow system here that can create additional complexity and additional richness in phenomena. What I want to talk today in the presentation is basically just these two feedback loops here between broadband turbulence in the zonal flows and fast particle modes in the zonal flow. I won't talk about gradient drive or fast particle driven PG mode, the physics and complexity associated with that. And there's quite a bit of work that has been done. Here's an example. I will talk about this a little bit more later of the analytical work that has been done to understand these interactions. So going into the main diagnostics that is used for probing these phenomena here. This is Doppler backscattering. Doppler backscattering is a microgrid characteristic where we create an ensemble of full linear microgrid beams at different frequencies that are launched with the lens horn that's shown schematically here. And these microgrid beams, typically between 2 and 5 centimeters in width, can be launched at different angles to the last close flux locus here. And this allows you, by a refraction in the plasma, this allows you to approach the cutoff layer for different frequencies that is located at different radii for different frequencies launched, and then basically look at the backscatter return that is maximized near the cutoff layer, and then determine the amplitude at a particular colloidal wave number that is given by the Brock condition here. So when you do this for different frequencies here, you can actually measure equals P velocity as well as equals P shear. Equals P velocity is basically determined from the Doppler shift of the backscatter signal. So it's basically the frequency shift compared to the offered frequency here, divided by the wave number that is determined by the geometry and by the scattering angle alpha, by the launch angle alpha here. And then there's a contribution here of the phase velocity that is in many cases very small compared to equals P velocity, in particular plasmas that are fast rotating or have a strong zonal flow activity, the equals P trope is normally dominant. So when we do this with different frequencies, you get different refraction here of the different frequencies in the plasma. You can now form a differential equals P velocity, and then that's nothing else than equals P shear here. So basically by subtracting because the Doppler shift measured in one location minus the neighboring location divided by the distance here that is given by ray tracing, by essentially following the microwave beams with a ray tracing algorithm, you can determine the shear rate. That's actually a very useful measurement that's been extensively done in the air plasma in conjunction with the LH transition, but it can also be done to very positive effect in the core plasma. So the other thing you can do is when you have several microwave beams that are creating scattering in neighboring locations, you can extract the radial correlation lengths of the density as well as of the flows from the Doppler shift by forming essentially the correlation coefficient between these two neighboring signals. So now going into the measurements itself and the results themselves. So this is our plasma here, which is an upper single null equilibrium in the cross section, just to show the location of the different diagnostics. So this is basically the radial coordinate here from 0 to 1, normalized radial radius. This is the region that is diagnosed with CBS that I just showed in the previous slide. We on purpose try to avoid regions with low order rational surfaces because there can be zonal flow dynamics that is just related to the present rational surface that we want to avoid. And most of the alkane eigenmode activity is in the core plasma anyway, so this overlaps the region that we're diagnosing. We can also look at temperature fluctuations. In this case, it's a plasma that has a fairly low toroidal magnetic field of 1.2 Tesla here to increase the hot ion beta. And that's why all the C chords here are on the high field. So normally in a full field plasma, they would be on this side here. But we can, because there's essentially electron temperature is fairly constant on the flux surface, we can make the measurements on the high field side as well and for potential Presbol effects there. This is the beam emission spectroscopy array that I talked about before. That's an 8x8 array here that can look at essentially vorticity, you can look at eddies, you can look at Reynolds stress by looking essentially by performing a velocimetry analysis of the eddy dynamics within this measurement area here. And that's a very important diagnostics to use to really understand the detailed topology of the turbulence that we look at. So these are the main diagnostics that we use, mostly Doppler backscattering, to some extent also BES. And that's the result that I showed you already before. Here's also a simulation for beta that shows particular alkane eigenmode that was done by Mike Van Deelen to give you a little bit idea of the topology. So in this particular case, the mode is located pretty much around mid radius. There's elongation along the field lines. Phase velocity along the field is very large. And the toroidal mode numbers are typically in the low 10 range, like between 2 or 3 and 8 or so. And then the colloidal mode numbers, as you can see, are higher. So typically more like 10 to 30, 5 to 30 or so. And so that's basically the result that I showed you before with the broadband turbulence spectrum here and the TE fluctuation, density fluctuation spectrum on top. This is here identifying the different modes. So the lowest one here is n equal 4. That's the toroidal mode number. N equal 5, n equal 6. Not all of them are easily identified. This is done by toroidal Milnor-coil arrays that are based around the toroidal circumference of the machine. This particular measurement here done at 0.55 is BES. And here that's the result that I showed you already before that shows the anti-correlation of the shearing rate measured from BES and the fluctuation, low frequency fluctuation that we look now in more detail. So the first result that we found is that the shearing rate and the density fluctuation amplitude are almost perfectly anti-correlated. At this mid-radius here at 0.43, where most of the mode activity was seen, the highest amplitudes were seen. And that essentially very much suggests that shear flows actually control the turbulence. The turbulence is not completely suppressed, but it's reduced by about 50%. So that's a fairly substantial effect. So there's clear anti-correlation between the shearing rate and the turbulence level. So how do we know that these are zonal flows? When we we have the capability to do DBS measurements with two different arrays on opposite sides of the torus. So when you imagine if you wanted to follow turbulence along a field line, you would have post-measurement arrays on the midplane. The colloidal correlation length is much shorter than the displacement that a field line experiences by essentially going halfway around the torus. Then never measure colloidal correlation unless you're measuring on the same field line. For flows, this is however different because here because of the m=0 structure, you only have to basically measure in the flux surface. So as long as you can confirm for the same launch frequency, measuring the same density layer and the same normalized radius, you can basically easily confirm whether this is an n=0 mode by just basically comparing signals to the measures on both sides of the torus. This shows here the 4 neutral beams in the 2D and the 60 and 40-degree port that carries the two different DBS systems that both have 8 channels and launch 8 different frequencies. So this is the result that we find when we measure basically when we compare those signals and shearing signals that are measured here and on the other side. So they almost perfectly match here within experimental errors. So this basically clearly confirms that N and M are 0, so that these are the axisymmetric shear flows. And this has been done for several radii. And here you see the correlation rate. If you don't believe the picture before, this is basically the correlation coefficient between the body between the DBS systems is basically very high degree of correlation and no correlation delay. So this shows very clearly that these are basically axisymmetric shear flows. So there's one more important ingredient for confirming the zonal flow nature, and that is the mesoscale structure. So that these are essentially shear flows that are very localized radially. And what we find is that the radial wave number at mid-radius is about 1 to 1.5 centimeters, and that corresponds to about 3.7 centimeters in radial extent of the shear. And the interesting thing is when you look at neighboring locations, so this is basically now a measurement done with 3 different channels, and you look at the difference between channel 1 and 2 and channel 2 and 3, you see that the shear flows reverse. So the red measurement that I showed you before is 180 degrees out of phase with the one that is done at the neighboring location, like 3.7 centimeters apart. So this clearly shows the mesoscale structure, so that we basically have radial wave numbers that are in between the iron normal radius and the macroscopic gradient lengths. So that proves pretty unambiguously that these are zonal. So the question was, of course, do we get transport effects? We have looked at electron temperature fluctuation, and they actually increase also when the shear flows increase. So the shear flow here in the background level is essentially unable to really influence the local fluctuation spectrum. So that's our reference level. And then when we get these 40–50% increase in the fluctuation level in the low frequency spectrum, that's when you see the electron temperature go up here by about 20 to 40 degrees. So it's not a huge effect, but there's clearly an effect on transport that rearranges the gradient, and that's something we have to look in more detail. So then we get interested, of course, in the radial dynamics and propagation dynamics, and ultimately in causality of these phenomena. And to do this, the first thing we did to really confirm that the shearing rate is large enough to influence the turbulence, we looked at the ratio of the decorrelation rate of the turbulence and the shearing rate. And when you do this, you have to always use Lagrangian dynamics here, because you have, of course, eddies that convected with a very high local equal spin velocity. So the measurement location and the measurement radius that we have is a very narrow beam that is only 14 centimeters wide. And the plasma turbulence is convecting at a high speed past the measurement location. So to correct for this, we do this Lagrangian transformation of the autocorrelation time. So how is the autocorrelation time of the turbulence that is measured in the lab frame? And then we essentially translate this back to the plasma frame by making a correction that depends on the speed velocity and the width of the diagnostic microwave. So when you do this and compare this to the shearing rate that we have shown you before, there's basically the two rates are essentially almost the same at 0.43, so they're very close range, and it's very similar, indicating that shear flow potential is very large effective equivalent. This is not the case when you go to other radii. So if you go to smaller radii, 0.33, or large radii, 0.55, there's a large difference between the decorrelation rate and shearing rate. So here, for example, the shearing rate is way too small to influence the turbulence. And here it's about the ratio is somewhat more favorable, but still the decorrelation rate is larger than the shearing rate. So basically, this confirms the very localized nature of the turbulence suppression. So we can also plot this versus radius now. So this in green here is basically the difference in fluctuation, low frequency fluctuation level between times when the PE modes are active and times when the PE modes are suppressed. You can see here that there's about a 50% decrease in fluctuation level here at mid radius. And then the opposite behavior is shown in the ratio of the shearing rate over the decorrelation rate. So it peaks here at the radius that is found we find the most profound fluctuation suppression. Not much effect here in the edge where fluctuations are not suppressed. So this all pretty much fits together with the idea that the localized mid-radius shear flows, reverting shear flows or tonal flows that drive the background turbulence. So now we looked a little bit at the propagation dynamics, and we found that in order to really confirm that TEs drive the solar flow, so we looked at the propagation delay, and we found that there's a small delay when you blow up the time scale, and you look at this in the final time scale that we showed you initially. There's about 60, 50, 60, 70 microseconds delay between the density fluctuation amplitude from PE and the peaking of the acoustic shearing. So that means that essentially the peaking of the PE amplitude precedes the peak of the shearing rate. So that is an indication that shear flows are actually driven by the TEs. We also looked at this in terms of the phase relation between and the correlation between the low frequency turbulence and shearing rate. And here we find actually that there's a radially distinct behavior. So at large radii, this is the cyan line here, we see that the shear flows precede the turbulence suppression. There's always anti-correlation. So when the shear flow is large, the turbulence amplitude is reduced. But in this case, actually, the shear flow precedes the turbulence reduction. The opposite is the case. There are only very small shifts here, on the order of 60 microseconds or so. And they can only do this measurement with conditional averaging over several of these cycles. But at small minor radii, there's the opposite behavior, so that actually the shear flows peak after the fluctuation level has already decreased. So this would indicate that turbulence may drive shear flow at small minor radii, and turbulence may be suppressed by shear flow at large radii. It's something that we have to follow up in more of this detailed bispectral analysis. But there's these kind of distinct radial delays. So here's an initial bispectrum that shows that there's nonlinear interaction between PE modes and shear flows very clearly. So you see here, essentially the amplitude that is plotted here is proportional to the cross correlation between frequency 1, density fluctuation of frequency 1 times 2 times frequency 2 times the equals the shearing rate, the complex conjugate at the sum of the two frequencies. And so we see basically here clear peaks in the TE range, frequency range that indicates that different TE modes are strongly interacting. But we also see a peak here near 0. There's finite finite frequency resolution. That's why the peak doesn't appear as exact 0 here, but this is a very strong signal here that shows that there is nonlinear interaction with the flows. And then you also see a second smaller peak that is associated very likely with the GAM frequency and matches the GAM frequency that is calculated for this condition. This is all done from mid-radius where we saw the most profound interaction. So then we looked also at the Reynolds stress that potentially could be responsible for driving colloidal ion flow that creates the electric field and the change in the shearing rate. And one complication here is that we cannot measure the Maxwell stress. So this is basically the ion acceleration here. That's the Reynolds stress, and that's the Maxwell stress, and that's the ion flow damping rate. That's basically the flow damping rate minus the classical flow damping rate. When you compare these different terms, the first one is between 27 to 28 meters per second square. The second one more than accounts for that. So that's 2 times 10 to the 8, 5 times 10 to the 8. Damping is typically very small, which is typical for core plasma conditions. Collisionality is very small here. The temperatures are about 1 to 2 kilovolt. So that makes all sense. So the damping term is not really very important here. But to really confirm that there's driven the flow drive by Reynolds stress, you would have to be able to have some estimate of some determination of the maximum stress. So that's a potential complication here. But when you look at this interesting region here, and this is just the radial range that spans the BES array that can perform velocimetry and actually extract the Reynolds stress. This was done here basically for the times that the TE activity is strong, and then the times in between that the activity is not there or is fresh. We see that there's a large difference in Reynolds stress gradient, especially here in the 0.52 and 0.43 region, so about 4 centimeters apart here. And you can see that there's clearly a strong Reynolds stress gradient that can potentially account for colloidal flow strong enough to explain shearing rates. With the caveat that we don't have direct measurements of the Maxwell stress. So in summary, axisymmetric flow oscillations that are very clearly identified as zonal flows and intermittent turbulence suppression have been confirmed during multiple TE activity. Radial mesoscale flows with scales in between the Lama radial scale and the macroscopic gradients are most pronounced. At mid radians at high beta fast ion, and beta in plasmas that have lower beta phase fast ion and higher colloidal field. We don't have a scaling yet, but we have a couple of different cases that have field. Density fluctuation levels are nearly anti-correlated to localized shear flows. Density fluctuations are substantially reduced if the shearing rate is sufficiently high, so that it's larger than the background turbulence correlation rate. This is clearly satisfied in the mid-radius region. Regarding causality, we find clear evidence that oscillating shear flows are driven by TEs. There's some evidence that shear flow precedes turbulence branch at larger radii and lags turbulence branch at smaller radii. That will look in more detail. We find significant Reynolds stress gradient potentially sufficient to explain the measured shear flows. So a lot of theoretical work has been done. About that. Here's just an example of 3 publications that I had mentioned earlier. So the first one by Liu Chen and Zonka finds basically spontaneous zonal flow excitation enhanced by ion response. So this is basically a modulation model that basically finds sidebands to the TE modes, and then that TE modes are separated by zonal flow scattering. The microturbulence is not considered in this model. Yes, so this is not a model that really closes the loop in terms of the dual feedback loops that really exist between thermal particles, TEs, and drift waves. There's another work that has been done by Choi and Pat Diamond that looked into the effect of ion dilution on the separated drift wave amplitude with the Algebra model, and also the effect of dilution plus ion dilution on zonal flow separation. And there's basically a beneficial effect in the sense that both the turbulent separation is reduced and the zonal flows are increased. So this basically just treats particles as passive. So it's just looking at the dilution effects on the dispersion and on the zonal flow drift wave interchange. And perhaps the most advanced recent model by Jan and Diamond looks at zonal modes in a closed loop system that both includes the drift wave suppression and the trend that allows potentially transport area and alpha channeling, but also looks at the F damping and how the F damping controls the saturation. So this is a model that essentially includes both feedback loops. And of course, there are many other simulations, and a lot of other work has been done that is not referenced here. So these are just examples of ongoing modeling. So what do we do in terms of future work here? So we plan to do more quantitative analysis of the colloidal momentum equation to look at colloidal flow generation, see whether we really consistent with the Reynolds stress gradients across the whole interesting radial region. There's questions about the role of the Maxwell stress. There may be some possibilities to get some idea at least on the colloidal magnetic field, the CPS, that's essentially an extension of the DBS diagnosis that can look at magnetic field fluctuation. In terms of self-organization of the zonal flow microturbulent PE system, what are the relevant timescales that create the cycle phenomena that we observe here? Are there limit cycles? How is the PE mode structure affected by microturbulence CF in terms of scattering? And radial turbulence group velocity spreading, of course, is a measurement that can be provided by emission spectroscopy also that can help in this endeavor. So then, of course, that's scaling with sparse ion plasma parameters. Dominant turbulence mode is important. So we have not looked at this in detail here in terms of the gradients. Both the eta I and eta E are larger than 1, so most likely we have a mixed mode regime here between TE, TEM, and ITG. What is the radial cross rate dependence, and what are the effects of radial thermal transport? That's pretty much all I have here. So thanks very much.